So we're going to be starting chapter 8 in this today. And we're going to skip section 8.1 for now. If you're still following along in the book at all, we're going to start with section 8.2 from the book. But really the reason I'm starting with 8.2 is because I first want to talk about matrix operations before we get into the 8.1 content. So we're going to be defining matrices today, which is probably going to be a new concept for most of you. And then we're going to do some basic operations with them. We're going to add, subtract, multiply, and then also multiply matrices by a scalar and just multiply matrices. So first of all, what the heck is a matrix? And really a matrix is just a way to store numbers. It's considered an array of numbers. Is sort of the more formal name, but really it's just a bunch of numbers in kind of a list or other ways, but we'll come back to that. If you have looked into computer programming at all, you probably recognize this word array. So matrices are used quite a bit in computer programming. I don't have a really strong background in computer programming, so I don't know all of the different ways that they're used. But they are used there. Matrices also come up a lot in when we're talking about vectors. We're going to come back to matrices and see what they can do with vectors. And then as we talked about before, vectors have quite a few applications as well. So matrices will come up there. Matrices in a more general sense come up in quantum mechanics and physics a lot. And also matrices can be used in coding. So they're used by military personnel to send codes out. So there's a lot of different applications of matrices, but for now it's going to seem kind of strange because we're just going to throw out some matrices and talk about what we can do with them. And there's in terms of adding and multiplying and stuff, but we're not going to look at those applications just yet. So bear with me for a bit while we define matrices and know that there are applications coming down the works later on. All right, so first of all, let's just look at an example of a matrix before we get too much more into the nitty-gritty. So usually we use these sort of large square brackets for a matrix, and then we just start writing numbers in. So for example, let's say I have the matrix 5 is a number there, -2, 1, 8, I don't know, -6, -3. It doesn't really matter. So here's a matrix. Each of these numbers is an actual entry in the matrix. They're all distinct. They don't do anything to each other. This does not mean take 5, subtract 2, then add 1 and get whatever 3 plus 1 is 4. This is not that. It just means literally there is a 5 in this first position here. And then there's a -2 in the second one if you're going from left to right, or you might think of 8 as the second if you're going top to bottom. We'll talk more about that later on in the video. But really this just means that we have this number 5 is in that spot. Oops. And so that's all it means. So it's just a way to store a bunch of numbers. Now you can have hundreds of thousands of entries in a matrix, and that's where computer programming helps out. But we're just going to take a look more at these smaller matrices for now. So I'm going to undo these circles I made just because I don't want them to get in the way of stuff. So this would be an example of a matrix. You can have all sorts of matrices. We could have I like that 5 there. Let's do a different one. Let's start with 1 and then 8 and then 13 and 56 and I don't know, -16, -3. I can put a pi in there. I could put the square root of 2 in there. I could put whatever numbers I want, and I could have more rows if I wanted, more columns. I could do whatever I wanted in here. 73. I could put a bunch of zeros if I want. Put the number E. I could even put imaginary in there if I want, although we won't do that too much. So there's another matrix. Usually we use capital letters for matrices, so I might say, well, this would be A and this would be B. but it doesn't really matter too much. Just know that usually we use capital letters for matrices. So in general, a matrix A is given by the first letter I'm going to put is lowercase a. Well, they're all going to be lowercase a's in this whole matrix. And what we do is we denote the very first one as 1, 1. Actually, usually we don't use a comma, but for now I'm going to, and then I'll come back to that. But this represents that this is the item in the first row and first column. So notice that in all the previous examples, we have our columns. And we're going to have our rows. And we could have more than that as well. So that means that in the very first spot here, first row and first column, I have A12. The next, or sorry, A11. The next one is going to be A12. So this means the first row, but now the second column. And that's going to continue, that pattern will continue on forever. Now, I put the comma there just to kind of make things easier to start with, but actually we usually don't use commas, which looks confusing at first because now it looks like A with a little 11 next to it. So if you do end up needing, say, the 11th row and the 23rd column, you would actually do a comma there to avoid confusion. But when there's just two numbers, know that it's row and then column. So the next one would be A2 for the second row, and now the first column. And then this spot would be the second row and the second column. And we could continue this pattern for as many rows and columns as we need. So let's just say we go on forever. Let's pick a number to be the final one. So the very last item in this matrix is going to still be in the first row, but let's just say I have m columns. So I don't know what m is. It could be 3. It might not be a very large number. But just because we're generalizing, this would be the first row, and whatever m, in this case, this is the final. I'm just using m to represent the final column. And since the number of rows could be different, I'm going to use a different letter here. I'm going to call this n. But it's still in the first column, so it'd be N1. That would make this N2. Over here, we'd have the second row and the mth, mth column. And then if we continue this, the very last term would be in the nth row and the mth column. So this represents n row. So this is the final row and the m column. So in general, if I just pick some term in there, pick a term which I'll call A with little ij next to it, this would be the term in the ith row and jth column. Okay, so far just looking at a bunch of definitions, just so we can actually, you guys will know when I say I want to pick A23, you'll know what I'm talking about. So just start getting used to this notation. It goes row, column when you're in these numbers here. Now, the next thing I want to mention is, well, there's a few more things I would like to mention. There's another term called order of a matrix. And the order is, for this matrix I gave up here, in general, the order is, we say n by m in this case. So it's rows by columns. By the way, I will do another example to kind of cement all these terms, but for now I'm just going to throw all the terms out for you. So the order of a matrix is, we would say, n by m. And then finally, you'll hear the term the diagonal. I'll be using that at different points throughout the days. Not so much in this first lesson, but it's worth bringing up now. So let's go back to our general matrix. A11, A12, A21, A22. I'll do a few terms here. And then this might go all the way down to a n1 and a1m. Okay, so this last one is a, n, m. So if you think about the diagonal, there's lots of diagonals, right? There's this is kind of the diagonal terms. There's this one. There's, I mean, even you could do something like this. You can imagine lots of different diagonals. But what we're going to be using at different points, it's going to be useful to think of the diagonal as this. So it's all the A's where the row equals the column. So for example, A44 will be on this all the way up to, we could say ANN or AMM, whichever one comes first. I'm not going to put that to avoid some confusion. But the diagonal is all terms A, I. So same row and column. And I'll come back to this as well. Don't worry too much about it. So before I end this video, because I do know it's getting a little bit long, I'd like to do one more example where we actually go through all of these terms. So let's just let A be a matrix, which we saw before. So let's say, let's just do that first one. I'll maybe add a little bit to it. Doesn't really matter. Let's call this 5, -2, 1. We'll do 8, -3, -7. And let's do 6, 1, 2. Actually, let's add one more column. So let's call this 0, -6, and 4. I haven't used a 4 yet. Doesn't really matter. Okay, so the order of this matrix, notice that there are 3 rows and there are 4 columns. So the order of this matrix, we would say this is a 3 by 4 matrix. If I wanted to just pick out a couple of terms, I might say something like, well, A12, first row, second column, this would be -2, just to kind of point that out. This is the A12 term. Let's say I wanted, I don't know, let's do the A34 term. This would be 4, because that's the third row and the fourth column. So just picking out a couple of those to help you identify how that works. And then if I wanted the diagonal, I would be talking about the numbers along here. This is the diagonal. So 5, -3, and 2. So that would be, the first term is 5, -3, and then 2. So those are the terms on the diagonal. And that pretty much covers everything I wanted to talk about. Yep, I think that covers it. One last thing to mention, one last definition. A matrix is a square matrix if the rows and columns are equal. Meaning that n equals m in that first example of the general matrix. So all matrices in the form of order n by n or m by m, where that's equal. So 2 by 2, 3 by 3, etc. Square matrices are going to be really important later on when we start talking about inverses and determinants and other things like that. So that covers all of the basics. In the next few videos, we'll be doing more operations, more actual problems. We'll add, subtract, multiply, all that good stuff.